Standard conditions. Standard temperature and pressure are abbreviated STP. And we need to know what is standard temperature, what is standard pressure. Standard temperature is 1 atmosphere. Atmospheric pressure at sea level, 760 torr, 760 millimeters of mercury. That's standard pressure. The standard temperature is the freezing point of water, 0 degrees Celsius, or 273 Kelvin, 273.15 Kelvin. So anytime you see STP in a gas problem or anything involving gases, that's telling us what the temperature and the pressure are. Instead of saying the pressure was 1 atmosphere and the temperature was 0 degrees Celsius, they'll just say at STP. So you need to know this. We've talked about, yes, question.
Is STP 273 or 273.51?
I think it's 273.15 because that's 0 degrees Celsius. It's the freezing point of water. The book is being sloppy, and I copied their sloppy on my slide. I should fix that. We talked about molar mass. That's the mass of 1 mole, right? Molar volume is the volume of 1 mole of gas at STP. So the volume of 1 mole of an ideal gas, meaning a gas that behaves perfectly. Are there any ideal gases? Not really. But there, in certain circumstances, they behave pretty close. So how much volume would this occupy? Can we calculate that? Sure we can. PV equals nRT, right? So the volume is going to equal nRT over P. The volume of 1 mole. So what's N? 1 mole. Exactly 1 mole, because we're deciding. Exactly 1 mole, what's the volume? R is still R, 0.08206 liter atmospheres per mole Kelvin. Is that an exact number? No, it isn't. Here it's given to 4 significant figures, which is plenty for what we're doing, but it's actually can be calculated more precisely than that. What's the temperature at STP? 273. I'm going to not be sloppy. I'm going to put the 1.5 in there. And then I need to divide by the pressure, which is what? 1 atmosphere. So I've got 1 times 0.08206 times 273.15 divided by 1. 22.414689 liters. How many sig figs? The 1 mole is exact, the 1 atmosphere is exact. So I've got 4 sig figs here, and I've got 5 there. So we would say 22.41 liters.
In the book, they make the 1 mole atmosphere both to 3 sig by 1.00. Is that something not important on a test?
It's not important. So in the book, when they did this, they wrote 1 mole as 1.00 moles. And they wrote 1 atmosphere as 1.00 atmosphere. Because standard pressure is defined as 1 atmosphere, I interpret that as the 1 atmosphere is exact. And since we're calculating the volume of this hypothetical number of moles, which we're choosing, then I say the choice of 1 mole is also exact. I don't know why they did that, but. So how big is 22.4 liters? Kind of hard to imagine, right? It's like this big. It's like one of those big U-Haul boxes that you put like pillows and stuff in. You would never put books in there because nobody'd be able to lift it. But it's like a good-sized moving box. That's what 22.4 liters is. So the molar volume of any gas at STP is 22.4 liters per mole. This is often rounded to 3 sig figs. It's not exact. So that means that 6.022 times 10 to the 23rd molecules or atoms of a gas are going to have that volume, 22.4 liters. So the volume of a gas is dependent on the number of molecules. The mass of the gas, though, does depend on the identity of the gas. And this is a very useful conversion factor. So let's look at these balloons here. So here we have 1 mole of helium. At STP, it's occupying 22.4 liters. Here, a mole of xenon gas, 22.4 liters. A mole of methane gas, 22.4 liters. How much would this gas weigh, the helium? How much would 1 mole of helium gas weigh? 4.003 grams. Forget that it's a gas, forget standard temperature, pressure, anything like that, what its volume is. 1 mole of it weighs 4.003 grams. How about 1 mole of xenon? Yeah, 131.29, I'm going to call it 131.3 grams. And 1 mole of methane, 16.01 grams. You could do that calculation. So the volumes are the same, but the masses are different. The masses of the particles matter, but the volume of the individual particles doesn't matter because there's a whole bunch of empty space in there. Any questions? So, do you remember density? Density is mass divided by volume, right? So density is mass divided by volume. Densities for gases are usually given in units of grams per liter instead of grams per milliliter because they're so much less dense. And so using this unit gives us more reasonable numbers. So your book gives this equation, and it's perfectly fine. It's not the one I'd use, but if you like it, go ahead and use it. Density equals the molar mass divided by the molar volume. So the molar mass is the mass of 1 mole of gas, of the substance, and the molar volume at STP is 22.4. So you could calculate the densities of helium and nitrogen at STP, the molar mass divided by the molar volume, which is the same for all gases. And we get his voice carries. This density is 0.179 grams per liter. This is 1.25 grams per liter. The volumes of the samples would be the same, but the densities would be different because the masses of the particles are different. Okay? What I prefer to do, because I don't like memorizing extra equations, I just go back to density is mass over volume, and I say, well, I wasn't given a specific sample volume or mass or anything, so that means I can just choose my gas sample. I choose 1 mole because it makes things easy. What's the mass of 1 mole? Well, it's the molar mass. What's the mass of what's the volume of 1 mole at STP? 22.4. You're going to get exactly the same calculation. So you can do either way. They end up the same. It's just what is easier for you to remember. And then there's this one. So density is proportional to the molar mass. Makes sense because density is mass over volume, and it's the mass of the individual particles that comes from the molar mass. And so they do all this and derive this equation. Density for a gas equals the pressure times the molar mass divided by RT. You can use that. That's fine. But that's another equation to remember, and I'm not a fan of that. So that's not how I'm going to do the next problem. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. I look at this problem, I see, calculate the density, and I have to ask myself, what's density? Density is mass over volume. So I'm going to write density equals mass divided by volume. And then I'm going to write down these numbers that I'm given, because that seems like a good idea. 742 millimeters of mercury. Okay, that's a pressure. And then temperature is 45 degrees Celsius. That's my temperature. Okay, well, fine. I did that. I'm going to go back up here. What do I need? I need the mass of this gas, and I need its volume. I'm going to choose 1 mole. The density of a gas does not depend on how much gas you have. Density is the same regardless of how much of it there is. It's an intensive property. Choose 1 mole. Well, could I calculate the mass of 1 mole? Sure, it's xenon, right? So 1 mole of xenon times its molar mass, right? 131.3 grams per mole. I wouldn't even have to do this calculation. 131.3 grams. That's the mass. That was easy. How do we get the volume? Ideal gas law. So the volume is equal to nRT over P. We've done that rearrangement before. So what's N? 1 mole, exactly 1 mole, because I decided that I was going to do this for 1 mole. Well, what's R? Well, R is the same thing it always is, 0.08206 liter atmospheres per mole Kelvin. What's temperature? Well, it's 45 Celsius, but it has to be in Kelvin. I better convert that. .15. And again, with the temperatures and the sig figs, this is measured to the nearest 1 degree. So after I convert it, it should still have uncertainty to the 1 degree, or 1 Kelvin. So there's my temperature. I can plug that in. 318.15 Kelvin. And then I need to divide by the pressure. Can I divide by 742 millimeters of mercury? No, I have to convert that to atmospheres. So it's 1 atmosphere per 760 millimeters of mercury. 742 divided by 760. 0.976, 3 sig figs, 32 atmospheres. Zero 0.97632 atmospheres. Checking units. Atmospheres cancel, kelvins cancel, moles cancel. You get volume in liters. That's what we want. 0.08206 times 318.15 divided by 0.97632 equals 26.741 liters. 3 sig figs. Now I have the mass and the volume. Density is the mass, 131.3 grams, divided by the volume, 26.741 liters. .9101, 4.91 grams per liter. Any questions? Yes?
So whenever it comes to density, we can choose one mole.
You can choose 1 mole. You could choose 5 moles or 17.437 moles, but then you'd have to put those numbers in here. And 1's easier. Or if you like the equation, if you like this equation, you can use that. I just have a hard time remembering that one. Any other questions? So the molar mass of a gas. We're actually going to do an experiment where we calculate this. We can figure out the molar mass of a volatile liquid experimentally. So what we do is we heat a weighed sample. We weigh some liquid out so we know its mass. We heat it until it becomes a gas. We measure the temperature, the pressure, and the volume, and that allows us to calculate the number of moles. And then we have the mass that we measured, the moles that we calculated, and we get the molar mass. Let's do a problem like that. A sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 973 millimeters of mercury. Find its molar mass. Okay, so I would look at this problem and I'd say, okay, I need the molar mass. So it's kind of like that density problem. Well, what is molar mass? It's the number of grams divided by the number of moles, right? So do I have grams or moles? I have milligrams, which I could make into grams. So the molar mass is the number of moles divided by the number of grams. So I could convert 827 milligrams into grams. So that's going to be 0.827 grams. And then I need the number of moles. That's where we're going to use the ideal gas law. So what do I have here? I have a volume. Volume equals 0.27 liters, 270 liters. Yes? That's a very good question. It's not moles per gram, it's grams per mole. Yeah, grams per mole. Oops. 0.827. Thank you for catching that. So there's my volume. Temperature is 88 degrees Celsius. What do we need to do that? Convert it to Kelvin. So 88 plus 273.15. It's best if you just do that right away, because otherwise, once you get in the middle of it, you might forget. And that's probably the most common mistake students make in doing gas problems, is they forget to convert the temperature. And the pressure is 975 millimeters of mercury. Since we're going to use the ideal gas law, which has the constant in it, we have to convert it. If we were doing a simple gas law, millimeters of mercury would probably work just fine. But for the ideal gas law, it has to be in atmospheres. So 975 divided by 760. So 1.2829 atmospheres. So I need to find N. So PV equals nRT. That means that N equals PV over RT. So I put in the pressure, 1.2829 atmospheres. And the volume, 0.270 liters. And then I'm dividing by R, liter atmospheres per mole Kelvin. And the temperature, 361.15 Kelvin. I look at my units, and I've got liters canceling and atmospheres canceling and Kelvin canceling. I end up with 1 over moles, which is the same as moles. Be careful when you do this calculation on your calculator. We are dividing by both of these numbers, and a lot of students really want to multiply them because this is next to that and it's multiplied. If you want to do that, you can, but you have to put parentheses around the whole thing. You have to put parentheses around this times that. Okay? Otherwise, you're going to end up with the wrong answer. So I'm going to take this number times that number, and I'm going to divide by this, and I'm going to divide by that. 1.2829 times 0.27 divided by 0.08206 divided by 361.15. 0.011688 moles. If you got a large number, you're having a communication problem with your calculator. And you actually multiply by 361 instead of dividing by it, which seriously messes up your answer. This is the number of moles. It's a very small number. But we only had 827 milligrams of this substance. So it should be a small number. So we're going to take that number and plug it into our molar mass equation up here, like 0.11688 moles. 0.827 divided by 0.011688. 70.756 or 70.8 grams per mole. Is it a reasonable molar mass? Yeah. I mean, if it was an element, we can't find a gaseous element, but then this is at a somewhat elevated temperature, but it could very easily be a compound. What about if you came up with a molar mass that was 0.7 grams per mole? That's not possible. The smallest element is hydrogen, and it's diatomic, and its molar mass is 2 grams per mole. So nothing less than 2 grams per mole is possible. Any questions? You can do this problem using this equation if you have the density, but I just think that's too much thinking. Okay, so here's an example that's really relating to like an experiment, and we're going to be doing this, I think, next week. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. So we have a volume, we have a temperature, we have a pressure, and then we have the mass of the flask with the gas in it and the mass of just the flask. Calculate the molar mass. This statement, calculate the molar mass, is the key to the whole thing. That tells us what we need to do. Well, what's molar mass? It's grams divided by moles. Get it right this time. Molar mass is grams per mole. So we need the mass of the gas and we need the volume. No, the moles. What's the easiest one to find? The grams. So here we have flask plus gas. Here we have flask. So we need to take this number, subtract that number. They're not exactly stacked up, but I'm just going to do them that way, minus 78.416 minus 77.834 equals 0.582 grams. Both of these masses were 3 decimal places, and the difference is 3 decimal places, so all of those digits are significant. .582 grams. How do we get moles? Ideal gas law. The cool thing about gases is that they're easy things to measure that allow you to calculate the number of moles. You can't do that with liquids and solids. So that makes calculating a molar mass a lot more difficult. Okay, are my units okay on these guys? No, none of them. So if I convert 213 milliliters to liters, is it 213,000 or 0.213? 0.213. 100 degrees Celsius. Well, I have to add 273, so that's going to be 373.15 Kelvin. And this was to the nearest tenth of a degree, so that's to the nearest tenth of a Kelvin. 754 torr multiplied by 1 atmosphere over 760 torr. Remember, torr and millimeters of mercury are the same thing. 754 divided by 760. 0.992105 atmospheres. Now I can calculate moles. So N equals PV over RT. So I've got my pressure, 0.922105. Did you see what I did there? I wrote 922 instead of 992. I see that happening in your labs. You just copy the number down wrong. And that's why we write our numbers in our notebooks and keep our notebooks. Okay, so there's pressure. Volume. 0.213 liters. Divided by R, 0.08206 liter atmospheres per mole Kelvin. And the temperature, 373.15 Kelvin. So the 0.992 times 0.213 divided by 0.08206 divided by 373.15 equals 0.00690. How many sig figs? 3. 1, 2 moles. The liters canceled, the atmospheres canceled, the kelvins canceled. I end up with moles. So I put that number up here in my, under my mass, 0.0069012 moles. .333 84.3 grams per mole. There's our molar mass. Any questions? Doing a problem like this requires putting together several different ideas. You need to be able to think about perhaps picturing in your mind what's going on with the flask and the flask plus the gas, and how do I find the mass of the flask. You have to have this end goal in mind, and then identify the pieces you need to find, and then find both of the pieces. You need to watch out for units. There's a lot of little tiny details that add up to make it a complicated problem, but all the individual steps are very simple. It's just there's so many of them. And the only way you can get good at stuff like this is to practice, practice, practice.